All right, here is the long summary for section 1.4 from OpenStax PreCalculus book, where we're talking about composition of functions. That's a bit of a lie, composition of function, about functions. That's a bit of a lie. Really, in this section, we're talking about different ways to put functions together to make other functions. So putting together smaller machines to make bigger machines from the parts of the smaller machines. It turns out there's 5 different ways you can do it. But the first 4 are pretty easy. There's not a whole lot to it. The 5th one is composition of functions, which we'll spend most of our time on, and hence the name of this section. But the first 4 are adding, subtracting, multiplying, and dividing functions. So really for this for 4/5, I guess, of this section, all you have to do is understand some notation. Understand that when you see something like this written, that means this. Wait, what? This is a machine, f plus g of x. It is. It's all one machine. I know this looks like a weird way to name a function, but the name of the machine is f plus g, and the input to that machine is x. And it's all just one machine. But the way that machine is defined is in terms of these other machines, f and g. So let's give you an example. Maybe if f of x were equal to, I don't know, the square root of x, and g of x were equal to, how about x plus 2? Sure. I could define a new machine, and I'd call it f plus g of x, and it would be in terms of these two guys. So if I asked a question, like I asked you, what is f plus g of, I don't know, 4? You could answer this question. This is a machine, and I'm putting 4 into that machine. It's a strange machine. I don't have a rule for this machine. But I do know, just based on the notation, that it means this thing right here. So when you're asked f plus g of 4, all you need to know is you're really being asked what's f of 4 plus g of 4. You could think about this machine in terms of its parts. And the parts are f of 4 and g of 4. And f of 4 I can figure out, because here's f of x, here's a blueprint for f. And so I can figure out f of 4, just copy this thing everywhere I see an x, change it into a 4. I get the square root of 4. Plus g of 4, well, I can figure that out too. I have the blueprint here, changing all the x's into 4s. 4 plus 2 is 6. Square root of 4 is 2, and 2 plus 6 is 8. So f plus g of 4 would be equal to 8. Not that surprising, I guess, but really, if you didn't know what this meant, you might not be able to solve this problem. But now you do know, now you can solve this problem. Not the most interesting problem, yet I'm going to spend some time doing it again. Wait, what? If you're asked f plus g of 4, you can certainly do it this way. You can just make this translation and figure out f of 4 and add to that g of 4. And nothing special with addition there. You could do that for subtraction or multiplication or division. However, I want to show you another way you could do this. If you were asked what is f plus g of 4, you could invest some time to figure out a rule for f plus g of x. So you could say, all right, let's figure out a rule that would describe this machine. Because remember, this is just one machine. I know I told you to think about it in terms of these two machines, but this itself is one machine. And I come up with a rule for that machine because I know that this means this. So it's just f of x plus g of x. And since f of x is the square root of x and g of x is x plus 2, I could come up with this rule. I could say that f plus g of x is a machine, and its rule is the square root of x plus 2. If I had this rule for this machine, I could answer any question you want. F plus g of 4? Sure, no problem. F plus g of 4, just copy this blueprint right here, except everywhere you see the letter x, change it into a 4. You got the square root of 4 plus 4 plus 2. I get the exact same answer of 8 that I got up here, and really the logic isn't all that different. But this idea of first coming up with the rule of the function and then evaluating that new function will be more powerful. And in fact, we're going to be doing more with the red method than we are the green method. But really, all you're trying to get out of this is that there's 5 different ways you can put functions together. I've just talked about one of them. Fortunately, I guess, the next 3 probably won't even merit getting an example. They're pretty straightforward. This is also a machine, f minus g of x. Hey, take a guess at how that function's defined in terms of f and g. Bet it's f of x minus g of x. You are correct. What about this one? Looks like f times g of x. Bet that's f of x times g of x. Correct. Is there a fourth one you could think of? I bet you could. Bet you'd think something like this. And I bet your guess would be that's just f of x divided by g of x. 100% right. Here's the first 4 ways we're going to put functions together. There's 5. We'll spend most of our time on the 5th, this idea of composing. But before I get there, I want to talk about these first 4 because they're pretty easy, so I want to make sure they make sense to you. If I ask you, what is f times g of x, or just fg next to each other when you write 2 letters next to each other, the multiplication's implied. What's fg of x? What's just f of x times g of x? So in this case, it would be the square root of x times x plus 2. I could ask, what's f times g of 4? And I could say that's 2 times 6, because f times g of x is f of x times g of x. Or I come up with the rule of fg of x. A rule for f times g of x is the square root of x times x plus 2. And then replace all the x's in that expression with 4s to figure out what comes out. Much like I did here, there's the green way and the red way, and you can do either one. Before I move on, I want to make one more comment. These are machines. This is a machine. This is a machine. This is a machine. This is a machine. I know it looks like 2 machines, but it's not. It's just one machine. It's one machine that's defined in terms of 2 other machines, but this is one machine. And why that's important is I can ask you for the domain of this machine. Since it's a machine, I can ask you its domain. I can do that. And for these first 3 types of combining functions, the domain's really easy. To be in the domain of f plus g of x, all that you have to do is be in the domain of f of x and the domain of g of x. Which makes sense, right? If there's some number, maybe 7, I don't know, and that's not in the domain of f, then it can't be in the domain of f plus g of x, because f plus g of x is f of x plus g of x, and if f of x is undefined at some number, like 7, for example, I can't take undefined and add something to it, so this entire thing would be undefined. The domain of these first 3 is just the intersections, if you want to get really mathy, of the domains of the 2 functions that comprise it, that it's defined in terms of. By intersection, I'm just saying you have to be in the domain of this guy and in the domain of this guy. That's it. And that works for these 3. For this 4th one, it's almost the same. We want to start out with the intersection of f of x and g of x of their domains. So to be in the domain of this machine, you must be in the domain of f of x. You must be in the domain of g of x. But there's more to it than that. It also must be the case that g of that number does not equal 0. Because it would also be problematic if the bottom here were equal to 0, right? Like if f of x is undefined, undefined divided by anything is still undefined. If g of x is undefined, then some number divided by undefined is still undefined. But even if f of x and g of x are both defined, if g of x equals 0, that's bad because it would be a number divided by 0, which is also undefined. So in addition to just having to be in the domain of f of x and g of x, which was the criteria over here for these 3, it must also be the case that when you take that number and plug it into g, 0 does not come out. And you'll see some examples of this in the chapter, but I just want to talk about it now. Probably talking more than I should about these first 4. I want to move on to composition of functions. Composition of functions is the 5th way you can put together 2 pieces to create a new machine. And I have an example written here, so I guess I'll use this example. F of x and g of x. You might be asked to find f of g of x. That's how you say this, f of g of x. This is not a multiplication sign. It's like an open circle here, f of g of x. The first thing I would do is I'd kind of add a 5th thing up here, some notation that says f of g of x is really just f of g of x. Well, wait, what's that mean? Okay, so just like if you start me out with this notation, I think about it in terms of this notation. If you start me with this notation, I think it in terms of this notation. These notations on the right here make sense. This one we probably have to talk about a little bit. So let me draw you a picture of what's going on here. I have 2 building block functions, f of x and g of x. And what I'm doing is I'm taking this machine here, maybe in red, and I'm taking this machine here, maybe in green, and what I'm doing is I'm creating a new function, which I'm going to draw in blue right here, using those two pieces. So in blue is my function, and it'll turn out the way I write the thing in blue will be this, or as we saw equivalently, f of g of x. I'll talk about where that notation comes from in a minute. But really the thing in blue is the machine. You're taking numbers and putting them into the thing in blue, and numbers come out. But sort of behind the scenes, like this is a big factory and this is the conveyor belt, and you see stuff go in on the conveyor belt and then it disappears, and some crazy stuff happens behind the scenes and then something else gets kicked out. What happens behind the scenes is your inputs first flow into G, and then they go out of G, and the output from G becomes the input for F, which is kind of wild. And then that kicks up. Okay, we need to get some numerical examples here because it's getting really complicated. My function G is this thing. My function F is this thing. So maybe I take the number, I don't know, 2, and put it into this machine in blue. Well, when I put it into the machine in blue, it's 2 that flows into G. And if I put 2 into G, I have the blueprint for G right here. I just got to change all the x's into 2's. If I changed all the x's into 2's, I'd have 1 over 2 plus 3, in other words, 1/5. So what comes out of G is the number 1/5. But that's not the output for the blue machine. That's the output from the red machine, which becomes the input into the green machine. So what I'm doing is I'm taking 1/5 and putting that into the green machine. I'm not putting 2 into the green machine. I'm putting 1/5 into the green machine. And the rule for the green machine is 1 over x. So 1 over 1/5 is 5 here. So what I'm saying, whatever. What I'm saying is that f of g of 2 is equal to 5. Wait, where's the 1/5? I don't see that anywhere. You don't write that here because that's all behind the scenes. The machine in blue right here, its input is 2 and its output, I wish I had done this in blue instead of green, is 5. F of g of 2 equals 5. This is function composition right here. Takes a little getting used to. It'll turn out that its domain is really, really interesting. There's a lot going on with the domain of this function that we'll talk about in just a minute. But first I want you to understand function composition. And I also want to realize that I asked a stupid question here. I'm going to change this a little bit. When we get to the point where we work on these examples, 1 and 3 were the exact same, so I want to change it. Instead of f of g of x, like in part 1, I want to do g of f of x. Oh, those are different? Turns out they are, which is kind of interesting. So what I want you to get out of function composition is first, I want you to understand that it comes from 2 parts, but it is just all one big machine. And what we do is we run our inputs into this machine first. This was done purposefully, having the g on this side and the f on this side. When I ask f of g of x, my input is going into g, not into f. G comes first, f comes second. That might be a little bit counterintuitive the way it's written, because you see the f first here and the g second, but g goes first and then f comes second. Maybe that's a little bit, a way I can explain that is by using the alternative notation, this guy. Right? Remember, f of g of x is just f of g of x. That's another way you can write it right here. But maybe if you stare at this, you'd be like, yeah, I've been trained to work inside the parentheses, so I guess it would make sense that I'd start by doing g of x first and then f of that thing. Where this notation comes from is by putting x into this blue machine. Maybe I can write it right below. Put x into the blue machine, and I want to know what comes out. Well, it would be x that goes into the g machine. And if x goes into the g machine, g of x comes out of the g machine. And if g of x comes out of the g machine, then it's g of x that goes into the f machine. And the way I can write that would be, what would come out of the f machine would be f of this input. In other words, this guy. So the things to take from function composition is first kind of understanding this picture, this flow chart, this diagram that'll help you. Although you typically won't be drawing these for every picture, I think having that intuitive understanding will help a lot. Next, understanding that the order is really important, that this means this, and that what happens here is G goes first and F goes second. And I'll give you another example. Actually, we'll do it on 3 here, where we do the order in reverse. The last thing I want you to realize is just like we had 2 ways of doing this problem. So remember back when I was working on this and I figured out f plus g of 4 by doing f of 4 plus g of 4, and then later I got really clever and did it this way. What I did down here is analogous to what I did in green here, where I took a 2 and put that into the red machine first and saw what came out, 1/5, and then took that 1/5 and put it into the green machine. That's this method. It would be nice if there was a clever way to do it like there was over here, and in fact there is. I can, if I'm asked what is f of g of 2, I can change the question, and I can make it just like number 1 right here. I could change it, instead of figuring out f of g of 2, I could figure out f of g of x. Why would you do that? Well, the idea is if I can come up with a rule for this function, then I can evaluate that function wherever the hell I want. I could put a 2 into this function if I only had a rule for this function. Just like I did over here, right? I came up with the rule for this function, and I wrote it right here. And then I evaluated it 4 by just changing all these x's into 4s. That's what I'm going to do over here. So how do you come up with the rule of the function? Well, I'm going to do this slightly differently than your book, just a little heads up here, but similar enough that hopefully it won't confuse anybody. And actually, I want to color coordinate it a little bit. Here's what I'm going to do. I am going to figure out f of g of x, so that it matches up with this picture down here. So remember, when you're asked f of g of x, like number 1 asked, you can rewrite it like this. You can say, well, f of g of x is just f of g of x written in this notation. That's this statement here. But this I can figure out. Right? I know that g of x, it's written right here, is 1 over x plus 3. So what I could write is f of, and then instead of writing g of x, write what g of x is equal to, 1 over x plus 3. I'll throw an equal sign in here somewhere. And so what's the advantage of this, breaking up into these steps? Well, what you now have is f of something. You have a blueprint for f of x. F of x is 1 over x. So I could figure out f of anything. F of 7 would be 1 over 7. Just replace all the x's with 7s. F of 32/5 would be 1 over 32/5. Just replace all the x's with 32/5. F of 1 over x plus 3, no problem. I learned in 1.1 that not only can I put numbers into functions, I can put expressions into functions. All I got to do is follow the blueprint, and everywhere I see the letter x, replace it with 1 over x plus 3. So I guess if I'm trying really hard to color code this, I would say it is 1 over, and then instead of writing an x, I'd write 1 over x plus 3 here. This is kind of a mess. I'd like to simplify this. So from here, I'm going to say, okay, so f of g, kind of going back and forth between my 2 notations, is 1 over 1 divided by 1 over x plus 3. That is f of g of x is just x plus 3. All right, because this is, what I did here is I wanted to make it so it's a fraction divided by a fraction, because I know how to divide fractions. It's like multiplying fractions, but you multiply by the reciprocal. So I take the denominator here and I flip it upside down. I get 1 over 1 times x plus 3 over 1. If you multiply straight across, you get here. So what I'm saying is I have a rule for the composite function right here. F of g of x is just x plus 3. So if somebody asks you the question, what is f of g of 2? Just like we did up here, what comes out of this blue machine when you put 2 into it? Well, all I got to do is follow this new rule of the machine I have here and say it's 2 plus 3, which is 5. Get the same answer that I got here without doing all these individual parts, because I now have a rule for the machine. This will be a very powerful way of figuring out, of evaluating functions, coming up with these rules like this. Okay, something you have to be careful of here. What if I asked you, maybe this needs to be in red. What if I asked you to find f of g? So after this, you did all this same work, and I asked you to find f of g of, let's see, how should I do this? Of 0, maybe. That seems like an innocent enough question. And actually, that's not what I want to ask. Sorry. Let's do f of g of, I don't know, maybe -3. That seems like an innocent enough question, right? Because I have f of g of x right here. And just like I figured out f of g of 2 by changing all the x's into 2's, you might think that you can figure out f of g of -3 by just changing all the x's into -3's. Find f of g of 3, period. You might think it's 0. It's not. It's not 0. It's actually undefined. Why is that true? Well, you have to be really careful about the domain of composite functions. You have to be really careful about what numbers you're allowed to put into these functions. Think about going back to this flowchart. If you took a -3 and threw it in. If you took -3 and tried to throw it in, it would go into this function in red right here. And the function in red does 1 over x plus 3. So it would be 1 over -3 plus 3. But that's 1 over 0. That's undefined. My function would break in this step right here. I'd never get to this step, and I'd certainly never get to this step. I wouldn't be able to output anything. So you got to be really careful when you define a rule for a composite function. You want to make really clear what its domain is. And its domain is trickier than the domains up here. Up here, I just had to make sure you're in the domain of f and in the domain of g. That's not the case down here. Down here, I want to make sure you're in the domain of f, and you're in the domain of g, and you're in the domain of the composite function, which is kind of tricky. So really what I'm getting into now is this domain of composite functions. So I guess we got composite functions down. I answered this question. I had never answered g of f of x. I guess I could do that while I'm here, just to point out that it's a little bit different. I'll do it without the color coding and try to squeeze it in. If I was figuring out g of f of x, I'd first write it into the handier notation. Note that the order here is different than the order here, but I still work on it the same way. I work from the inside out. I know that f of x is 1 over x. So to figure out g of f of x, I take that 1 over x and put it into my g machine, which I can do because I have a rule for the g machine. G of x is 1 over x plus 3, so follow this blueprint, except everywhere you see an x, replace it with 1 over x. You'd get 1 over x plus 3. Similar to, but not the same as what I got over here. I can prove that's different by doing a little simplification. If I got a common denominator here, my least common denominator would be x. So instead of 3 here, I think about it as 3x over x. So I'd get 1 plus 3x over x. And if I think about this 1 as 1 divided by 1, now I got a fraction inside of a fraction. I can flip it upside down, and I get x over 1 plus 3x. Very different than what I got right here, x plus 3. My point is that when you compose functions, function composition is not commutative. Throw some math terms around. When you compose them in a different order, f of g of x, generally speaking, is not the same as g of f of x. One was this, the other was this. So that's an important point, and now I can move beyond. Now I've done 1 and 3, but I haven't talked about 2 here. So kind of going in a strange order, but let's talk about 2. Let's talk about the domain of a composite function. There's a rule. To find domain of f of g of x. Or how about just f of g? To find the domain of this composite function here, what do? I'm going to break it down into a multiple step process. I'm going to say step 1 is exclude anything that is not in the domain of g. F of g of x. You exclude anything that's not in the domain of g. So in this example up here, maybe in red I'll do my example. in example, I get that x cannot be equal to -3. Because my function g right here, its domain would be all numbers that don't make me divide by 0. And the only way I divide by 0 is if x plus 3 equals 0. And the only way x plus 3 equals 0 is if x equals -3. So I'm going to exclude -3. Step 2. You're like, hurry up, I get step 2. Step 2 is going to say exclude everything that's not in the domain of f. No, in fact, it's not. It's totally fine to have numbers in the domain of f of g that are not in the domain of f. And that might be a little bit confusing. Okay, so first of all, the number 0 is not in the domain of f, right? Because if you try to put 0 into this machine right here, it'd be 1 divided by 0, which is undefined. But check out what happens if you put 0 into the composite function. If you put 0 in blue right here, then that 0 flows into the red machine, and I'd get 1 divided by 0 plus 3, which is 1/3. So 1/3 would pop out here, and that would go into the green machine, and it's totally fine to put 1/3 into the green machine. It doesn't break. So 0 is in the domain of this blue machine right here, which is a little bit surprising, because it's not in the domain of this green machine. And the reason why the domain of the green machine is not relevant to the domain of the composite machine is the inputs into the composite machine do not go directly into the green machine. They go into the red machine first and then into the green machine. So really what you have to figure out is by checking in step 1 here, the domain of G, I'm making sure the machine doesn't break in this step. But it might also break in this step. What will break it in this step are if the output from the red machine is a number like 0, is a number that'll make me do something illegal, that'll break this machine, in this specific case, make me divide by 0. So how the hell are you going to figure that out? I mean, I guess there's a couple ways you can do it. You can try to talk yourself through it. But with complicated functions, it can be really hard to talk yourself through what you would have to put into red to make something come out that would break the green machine. So what you do is you exclude anything that is not in the domain of the composite expression. The hell am I talking about? Give me a second. Of the composite expression. So what I mean is if we were trying to figure out the domain of f of g, this machine pictured right here, what you would want to do first is answer question 1. Find f of g of x, which is what I did over here, and come up with a simplified form of the composite expression. The composite expression is f of g of x equals x plus 3. And in this specific example, there's nothing to exclude. It's not always the case, but in this specific example, there's nothing to exclude. Because if you think about this as a machine, well, it will never divide by 0 because there's no division sign with an x in the denominator. And there's no square roots or fourth roots or even roots. So I don't have to worry about taking the square root of a negative number. There's nothing to exclude here. So to figure out the domain, the domain of f of g is everything from -infinity up to -3 and everything from -3 up to infinity. The only number I had to exclude in this specific case was -3 because when you're finding the domain of a composite function, you have to check 2 things. You have to check the domain of the inner function, the second function listed in this notation, and then you also have to check the domain of the composite expression. Nowhere in here, maybe I'll even write, note, the domain of f is not relevant. You do not care about the domain of the outer function. You take care of that when you're looking at the composite expression. You care about the domain of the inner function and that. So that'll help you find the domain. I guess I could do this again while I'm here since this is the long video. Let's do one more domain problem, then I'll talk quickly about decomposition, then we'll call this good. the domain of, I just did f of g, so how about g of f? From step 1 here, I'd want to exclude anything that is not in the domain of f this time, because f is the second function written. F is the inner function. So what numbers are not in the domain of f? Well, here's f right here. 0 is the only number that's not in the domain, so I get x does not equal 0. And then what I have to do is exclude anything that is not in the domain of the composite expression. Well, fortunately, I already did all this work to get the composite expression right here. The composite expression is x divided by 1 plus 3x. So I got to figure out what numbers are not in the domain of the composite expression. Well, what numbers would make me divide by 0 here? I divide by 0 if 1 plus 3x were equal to 0. In other words, if 3x were equal to negative 1. In other words, if x were equal to negative 1/3. So from my second step, I decide to exclude negative 1/3. So my answer would be all the numbers except for 0 and negative 1/3, which in interval notation you can write like this. A little bit hard to read this here, but it's everything that's less than negative 1/3, everything between negative 1/3 and 0, and everything that's greater than 0. All right, finally, the last topic in this kind of a meaty section is this idea of decomposition. So I guess I've talked about domain of a composite function. The last thing I want to talk about is decomposition of functions. Essentially, what you're doing here is you're working backwards. So you're given the answer and you're coming up with the question. Think Jeopardy, I suppose, if you watch Jeopardy. So I have some function, maybe I'll call it h of x. And let's see, here's one that's similar to an example from your book. 1 minus x to the third power, sure. This is a perfectly good function, right? What you're doing with function decomposition is you're trying to rewrite this function in terms of two smaller functions, f and g. So h of x equals this, period. Express h as f of g. So come up with two pieces, f and g, so that when you put them together in this fashion, this right here is your answer. Takes a little doing. The first thing to know is that anytime you're doing this is what's called decomposition. You're not composing them together. You're decomposing this thing to come up with your answer. The first thing to know is there's multiple different answers. So let me first just show you a couple of answers and then explain how you could have come up with those answers. One possible answer is you could say f of x is the square root of x, and g of x is 1 minus x cubed. And how do you know that's right? Well, I mean, probably the easiest way the first time you learn this is almost a guess and check way. I see this square root and I see this 1 minus x cubed. I wonder if I made it the square root of x and 1 minus x cubed, what would happen? Well, let's see, f of g of x, let's figure it out. Let's see, how do I color code this? Maybe let's write it like this. F of g of x. The second one maybe should have been red. Maybe I'm caring too much about parentheses. Would be the square root of, no, let's do it in steps. Settle down. Would be f of and I know g of x is 1 minus x cubed. So all I'm doing is replacing what's in green here with 1 minus x cubed because that's what I think g of x might be. And then how do you go from there? Well, I know that f of anything is just the square root of that anything. I have this blueprint for f of x, so if I'm asked what's f of 1 minus x cubed, I would just say it's the square root of, and then instead of writing x, I'd write 1 minus x cubed. I'd copy this thing, and everywhere I see the letter x, I would replace it with 1 minus x cubed. And I would get exactly this. Oh, cool. Put a little check mark by it. It looks like this function decomposes into these pieces. So my answer would be something like, so f of x, well, I guess it's what's written above. So my answer would be f of x equals this and g of x equals this if I want to express h in this way. Okay, I mean, that's cool and all. I didn't really give you a way to do it. I told you the answer and give you a way to check your answer, which is a little frustrating. Another thing that's frustrating is there's many different answers for these types of problems. So let me spit a couple more out at you and see if you believe me. I also could have said that f of x is equal to the square root of 1 minus x. And g of x is equal to x cubed. And I think if these are your choices for f and g, and you compose the two of these guys together, and maybe you're getting to the point where you're really good at function composition, and you can just look at these, you might be able to tell that you get the same answer. Other possible answers, if you're asked this like on a test, there's always the trivial decomposition. I don't know that I should be making this as a way to do it, but sure, it's right. I mean, your teacher might get mad at you for doing this kind of trivial way of decomposing these two guys. But we can always do this thing. F of g of x. Well, f of x is just x. This f function, all it does is spits out as its output exactly what the input is. So if the input is this entire thing, then composing those together, I'd get the answer. I could do another trivial decomposition by saying f of x is the square root of 1 minus x cubed, and g of x equals x. So my point is that like this is a perfectly good answer, as is this, as is this, as is this. A teacher's probably looking for something that looks like this or something that looks like this. And so if you see notation like find a non-trivial decomposition for this function, then you couldn't use either of these two answers. But if your teacher doesn't tell you that, you could certainly use those right there. Here's one more just because I think is kind of cool. If I made, sure, I guess I can throw it right here. Let's make f of x equal to, which order should I do this in? I want f of g of x. So let's make f of x, x plus some number, whatever your favorite number is. 23 from Michael Jordan, maybe. And g of x is the square root of 1 minus x cubed minus 23. Note that minus 23 is not underneath the square root sign. Then when I do f of g of x, all I do for f of g of x is it's f of all this stuff. So take all this stuff and put it in place of the x right here. You get all this stuff plus 23. The minus 23 and the plus 23 would cancel out. You get the same answer. So lots and lots of different ways, maybe there needs to be another or in here, of answers for possible decompositions, which I guess is fine. For what it's worth, you're learning this for a calculus class, and in the calculus class, it won't help you at all to use the trivial decompositions, nor will you want to use some strange thing like this where you just pull a 23 kind of out of nowhere. I mean, it's correct, it's a decomposition, but it's not a useful decomposition. The useful decompositions in this case would be this one or this one right here. They're both useful in their own right. So I don't know, if you're really just trying to give the teacher what they want, give this as an answer or give this as an answer. If you can come up with that, what you're able to do is you're able to decompose functions. And I know I didn't really give you a great way to do it. There are some methods, but I don't think there are any that are really better. If you're just told to decompose, I think it's kind of a guess and check game that's more of an art than a science. And so you just kind of get the hang of it. Take some guesses of what you think the answer is, compose them back together. If you're right, fantastic, you're done. If you're wrong, kind of figure out why you're wrong, and that might help you, might educate you on making future guesses so that you won't be wrong next time around. All right, kind of a long video, so I'll end this thing here. That's section 1.4 from PreCalculus.